The fundamental theorem. So, we've learned in the previous chapter that to calculate the area under a curve, you can simply calculate the antiderivative and calculate um, the upper bound and the lower bound and find the difference between the two. The reason it works is actually quite intuitive, and it's because the area between these two functions is given by the change in the original function. It's a little bit hard to understand intuitively, but essentially, if the area here, so like let's say this is velocity, let's say this is a velocity function. If the area under the velocity graph gives you the change in displacement, uh, then the area would be equal to delta antiderivative or delta integral of the velocity function. Simply because the area under the curve is just giving you the change in distance because you're summing up these individual velocity times time using Riemann sums logic. So because of the summation of the velocity of the product of velocity and times, you are given the change in distance or displacement in this case because we're dealing with velocity. And as a result, you get the area under the curve equal to the change in velocity, a change in the integral of the velocity function. And as you can see, you get a constant of integration. But since we're dealing with the same function, typically they'll just cancel out and give us the definite integral. And what does the fundamental theorem of calculus say? So now we understand that the area under curve is equal to change in original function. And I say original because we can deal with a lot of functions. We can deal with velocity functions, a power function, a power function as in the rate of work over time. We can be dealing with other scientific functions that have a first and second derivative. But typically, calculus, like with Newton's discoveries, came with the discoveries of physics, not necessarily math. Well, math, of course, but it was usually to help discover physics problems. I mean, he worked very closely with Bernoulli and other scientists, actually not really closely, but he was within that field. And in fact, Johann Bernoulli says that he recognized the line by his claw because Newton solved his work in one night and sent it back. The area of the curve is a change in the original f delta x. How do we write that mathematically? And about the area under the curve, let's just say f of x is equal to delta f of x. And if we plug in bounds, so a and b, then we get the integral of a and b of f of x equal to f of a minus f of b, where f of x is defined as the integral of f of x, or this is where the fundamental theorem of calculus comes into play. A d of x is equal to f of x equals integral of x. So integral is equal to the function. So in physics, it would be the derivative of position, which I don't really know. S of t is equal to v of t, and the derivative of velocity is equal to acceleration. How fast the velocity is changing is just acceleration. So yeah, that's the logic behind it. But now I didn't really memorize the FTC word by word or the exact theorem. There's very few theorems I could state word for word, but I do know what it says, and it essentially states that the derivative of an integral is just the integrand. That's literally all it means. But they have like a complicated thing. Like for example, the precise definition of a limit is that for every delta that is greater than zero, there must exist an epsilon, such that the difference between the function and the limit is less than epsilon, and the difference between the two inputs, absolute value, of course, is less than delta. In this case, I don't know the exact thing, like I said, so the derivative of an integral is equal to the integrand. That's essentially what it means, and we can use some logic to figure this out mathematically or however you want to do so. So the derivative of an integral is just going to be d of dx of the integral of f of x dx. I guess I was forgetting to put the dx in all the prior notations, but in this case it doesn't matter. Now logically you can look at this and say the dx is cancel out, but I mean math is not that simple, of course, and you can't just do it. That's like doing 6 divided by x, and then saying that's equal to 6 divided by x, and then crossing out the x's. It's not really that intuitive. Although technically it does work, much like the chain rule where you can cross out the dx's on the top and the bottom. However, in this case, we can just use some logic. So as we know, we defined the function before as equaling the antiderivative at one point minus the antiderivative at the other point. In this case, it's a definite integral, which essentially just means x at 0. It's going to be f of x plus c, because f of 0 wouldn't always be 0, but we are calculating the indefinite integral here, so it doesn't matter. And if you differentiate this, remember that d of x of the antiderivative gives you the derivative, and it's pretty logical. Differentiating an antiderivative will give you the original function back. And c is just a constant of integration, which should give you the f of x back. And notice that these are the same thing. So we notice that the integrand just stays the same. So the derivative of any function, which is just going to be f of t. Let's just use t as the variable. Actually, that wouldn't make much sense. I just kind of wanted to relate it to physics, but in this case, it wouldn't matter. We'll always just equal f of x, which is pretty intuitive, and we can use some logic for this. And I'm just going to make a few practice problems. For example, we can set a function equal to x cubed, and we'll say the integral of f dx with respect to x, obviously, which is x cubed dx. And then let's say, if we integrate it out, we get x to the fourth divided by 4 over, or not over, and well, it's an indefinite integral, so no bounds are needed. We'll always don't forget the plus c. Again, c is just an arbitrary constant, so technically the difference between two integrals will not always give you the same constant of integration. You just always need a constant of integration regarding integration. And with the function x to the fourth power plus c, if you differentiate it, you realize that you get the original function back. So let's do the integration. 4 comes to the bottom. 4x cubed divided by 4 plus c. Well, everybody knows that the derivative of constant is just it's irrelevant. It becomes 0, so it becomes x cubed, which is the exact same thing. Now, it does get a little bit complicated when you are doing different things, like different bounds. So for example, if you're doing the integral of x squared of x of, let's say, x squared, just to keep things a little bit simple, because we're only going to be dealing with subtraction and addition of powers, we're going to get, well, we got to do the antiderivative first, and then we got to plug in the up. There's going to be x cubed to the third minus 3 minus x4 to the third, technically with the difference of the constants of integration, but they just cancel out. So this is what you're left, and let's differentiate it. We're going to get obviously the fourth divided by third, which is going to be 5. Well, yeah, you can't really simplify that actually. And to the third over 3, which is approximately 1.333 x cubed. And as you can see, it's not the exact same because we are not dealing with x. So I guess the more precise definition would be if it is an indefinite integral regarding the value of x, without the upper bound being some specific variable, then d of dx of the integral of any function is equal. Actually, why do I keep is equal to the integrand itself? And that's pretty logical. And again, the logic behind it is, let's take a graph. Let's say that this is a velocity graph. You're moving at 5 miles per hour here. Let's say 10 here. And let's say that it's like a parabola. This kind of looks like an error function actually, but we'll say that it's 5 here. So 5 times, let's say this is 1 hour, Riemann sums, of course, 5 times 1, that means you traveled 5 meters. That means the change in displacement is equal to 5 meters, which means that that would just simply be equal to the height here of the original function. It's a little bit hard to draw abstractly because we don't know where the original function is with the constant of integration. But all we do know is that the difference is going to be 5 greater because we've traveled 5 meters per hour for 1 hour in this case. So that is the logic there, and that is the fundamental theorem of calculus, essentially.